So first, I would like to thank the organizer and Meir and Vanderlei for having me there and organizing this nice workshop. So I'm a member of the Bose-Einstein condensate group in Paris 13 University. So we are located at Villetaneuse. It's just north of Paris. And in this talk, I will be presenting our results about the collective excitations of superfluid Bose-Einstein condensate or superfluid Bose gas. And so in my talk, there will be only mean field, or I would say most of the effects I will present are well captured within the mean field description, so the Gross-Pitaevsky equation. And basically the outline is like this, following this picture. So I would like to show how we are able to experimentally observe and image the collective excitations of the system, and then use some of these excitations to measure the superfluid response. And finally, I will be going to the last two pictures that are what happens when we make the gas rotate and eventually achieve such fast rotations that the gas is flowing around the trap minimum with a giant hole. So the shape of the trap in this last picture is still a single minimum trap potential, but due to the fast rotation, the centrifugal force makes the atom rotate on this ring shape. So first I would like to introduce this subject by just recalling some interesting facts about superfluidity. So there are many spectacular properties associated to superfluidity. One of the most prominent is the Fontaine effect in helium due to the absence of viscosity, and so the fact that this fluid can climb up the walls of the bottle. And for our systems, this kind of absence of viscosity is well captured by the notion of critical velocity, so the so-called Landau criterion, that says that if you have an impurity moving into the gas, you need to go beyond a given finite velocity to excite the gas. So if the impurity goes too slowly, there won't be any excitations in the gas. And then when you have a superfluid, what you can do is try to trap it in interesting geometries, as was done in the group of Gretchen Campbell at NIST. And for example, they were able to create this kind of circular waveguides, if you want, where the atoms can rotate in such circular traps. And they can then add, for example, like tunable barriers at some point that create weak links and control the transport properties in such a device. So the interesting thing here is that we know that because it's a superfluid, there is a quantized circulation in the system, and so the flow is quantized. And another illustration of this quantization of the flow is as we have already seen earlier this week, is the occurrence of vortices when you try to make the gas rotate. And I will talk a little bit more about this later on. And then the first subject I will be talking about will be this kind of collective excitations of the gas. Mostly you observe them when you trapped the atoms, the gas in a trap. Okay, so I will talk about the superfluid dynamics, and first I would like maybe to comment on what is for us a quasi two-dimensional system. And I would say that in our case it's a matter of energy scales. So we describe this kind of 3D to 2D crossover by comparing energy scales in our system. And the first energy scale is the temperature. So if you want to achieve a two-dimensional regime, what you need to have is an anisotropic trap where one of the trapping frequency is much higher than the others. So in our case, it will be the vertical trapping frequency, omega z, that is much larger than the other two trapping frequencies that are of the same order of magnitude. And then what happens is that you need to take into account the discrete nature of the spectrum along the vertical direction, so you cannot neglect the fact that it's discrete and treat it semi-classically. And if you compare the temperature to the typical trapping energy, so h bar times the trapping frequency, if you have a temperature that is much below this value, then you can say that you don't have enough energy to excite the system, even in the first excited state. And therefore, all the dynamics will occur in the NZ equal to 0 manifold. And it turns out that this is quite a difficult condition to achieve, to have a temperature much below the trapping frequency. But in this case, we have a little help from the Bose statistics. The idea is that even if the temperature is of the order of the trapping energy or a few times the trapping energy, we benefit from the saturation effect due to the Bose statistics. So the idea is that you have this kind of two-step condensation phenomenon in this case, where as soon as the temperature is close to the trapping energy, you saturate the number of atoms in the excited states, and as you add more and more atoms, they will only go in the NZ equals 0 manifold. So the idea is that the system is never truly 2D, but the atoms that are out of the first, so the lowest level of the trapping potential, we know how to deal with them. It will be a dilute gas of atoms that are, so in some, that populate some of the excited states of the system, but that will be basically non-interacting and only filling the interaction energy or interacting with atoms in the ground state. So we can, if you want, kind of remove them from our, from the picture. And then, as we add atoms in the ground state of the vertical trapping potential, we have a second energy scale that starts to matter. It's the energy scale associated to the interaction energy. So in this case, we introduce this dimensionless interaction factor, that is the ratio of the scattering length, the low energy scattering length in the S-wave, for the S-wave collision, to the typical size of the fundamental state of the Z trapping potential. And what happens is that if you start to have many atoms, so the interaction energy rates like this dimensionless interaction strength times the two-dimensional density, and at some point it can be comparable to the trapping energy or even larger than the trapping energy. And in this case, you will have a dimensional crossover, this time induced by this new energy scale, the interaction energy. And in fact, what happens also is that we have a little, so the situation is a little bit more favorable than for the temperature, because due to symmetry reasons, in fact, with two-body interactions, you cannot populate directly the first excited state of the potential, but only the second excited state. So you have only to take into consideration what happens for the second and the fourth and so on excited states. So in our system, we will have a typical temperature that is of the order of magnitude of the trapping energy, and an interaction strength that is below the 2 times the trapping energy, and this will be a quasi-2D Bose gas for us. Yes?
What do you mean by semi-classical potential?
I mean that we don't need to take into account the discreteness of the spectrum, and that we can treat everything like a continuous potential and a kinetic energy operator. So if we don't have to... it's a semi-classical description of the dynamics. Yeah. Yes, exactly. So what is so interesting about two dimensions, and we heard before this week that the way to go was to study homogeneous systems, and that traps are most of the time maybe like hindering some subtle effects or masking the what we want to see. So I would like just to comment on that. And in 2D, what we know from the theory is that if you have a non-interacting gas, so ideal Bose gas in a homogeneous infinite-size system, well, you don't have Bose-Einstein condensation, and you don't have a superfluid. So it's a kind of boring situation. What's more interesting is if you start to add interactions, there is this well-known Berezinski-Kosterlitz-Towles mechanism that comes into play, and that will give you a crossover to a superfluid phase for sufficiently low temperature, and this has been, for example, evidenced in an experiment at Collège de France and ENS. Now, if you add the trap, what you get from the trap, so I'm talking about this trap in the transverse direction, so in the lowest state of the vertical potential, so the trap in the XY plane will give you an energy scale that will again enable Bose-Einstein condensation just as a finite size effect in the system, in fact. And still, if the system is not interacting, you don't expect superfluidity. And when we have both a trap and interactions, we will have both mechanisms coming into play. So, and this has been probed in Zoran Hadzibabic's group in Cambridge, where they tuned the Feshbach resonance to go from the two-dimensional trapped ideal to interacting gas, and they have seen quantitatively how the system goes from the Bose-Einstein condensate mechanism to Berezinski-Kosterlitz transition. So just to recall some facts, so I won't be really using this in the rest of the talk, but just to give some order of magnitude. So the interesting fact point in 2D is that you don't have a typical length scale if you write the Hamiltonian, so you get this dimensionless interaction strengths, and then everything can be, so you have a scaling symmetry that makes the system invariant, and then you can show that the equation of state depends only on two parameters, this dimensionless interaction strengths and what we call the reduced chemical potential, so the ratio of the chemical potential to the temperature. And for our setup, you have the numbers there. So the typical critical density for Berezinski-Kosterlitz is about 8 in the phase space density. So why the trap are so interesting in this kind of setups? Well, we heard already about local density approximation in previous talk, and this is really useful for to probe this 2D physics. So the idea is that when you have a trap that is shown here in black, a trap potential, and you have a given chemical potential related to how many atoms you have in your system, then you can define a local chemical potential by subtracting from the maximum chemical potential the trap energy. And local density approximation tells you that if it works, you can describe the system at one position as the homogeneous system, the unequivalent homogeneous system with this particular chemical potential. And so this is an hypothesis that LGA will work in such system, but in fact it has been shown using quantum Monte Carlo simulation that it was kind of very accurate description of what happens in these traps. And now the idea is that with a single realization of two-dimensional Bose gas, you are able with a single image. So what you do is you you measure the local density, so physical two-dimensional density of your system. You measure independently the temperature, and for those both measurement and the knowledge of the trap shape, you can infer what is the value of the local chemical potential and the value of the local phase space density. And when you do this, you see that all the points that you can take from a single experiment and for different experiments in different conditions fall on a single universal line that is exactly, let's say, within experimental error bars, the equation of state of the two-dimensional Bose gas. So this has been shown in Jean Dalibar's group a few years ago. So this is one of the interests of using a trap, for example, in this system, if you want to measure the equation of state. And if you don't have a trap, then you have to do many, many experiments with many different number of atoms, for example, to span the whole range of chemical potentials. Okay, so now I'm coming to the core of my talk. So the superfluid dynamics, what do we expect in 2 dimensions? And I would like to recall 2, let's say, landmark experiments. So the first one is quite an old one, and it evidenced the 2-dimensional transition, Brzezinski-Kostler transition in helium-4, using this measurement, using a torsional pendulum here. So it's a pendulum that will rotate around its axis. And as you lower the temperature in the system, you see that here it's the period of the oscillation that is plotted. You see that the periods start to deviate, and there is an abrupt jump of the period at some critical temperature. So the period is increasing, and the frequency is decreasing. And this is associated, in fact, to the superfluid transition of a thin film of helium adsorbed on the surface of these plateaus of the torsional operator. So this was the first demonstration of Brzezinski-Kostler Thouless transition in this setup. And more recently, we have a very nice measurement, again in Jean Dalibar's group, where he probed the Landau criterion for this system. So the idea is like this. You create with optical beam very tightly focused a defect in the gas, and you rotate the defect around the gas that has a cylindrical symmetry. And what they see is that if the defect is rotating close to the center, where the density is high and where you expect the superfluid to be, there is a threshold in velocity of the defect to create excitation. So they probe very locally the gas, and they measure global response by the increase of temperature in the system. And what they show in the paper is that if you repeat the same measurement but far in the wings of the gas, then you don't see this critical velocity effect, and whatever the velocity, you always excite the gas. So the message is that there is a superfluid at the center of the gas, and there is a normal fluid on the edge. In the following of my talk, I will be kind of revisiting this experiment, but trying to make the same experiment as this one in our gas. Okay, so our experiments is like this. So it's a rubidium condensate experiment. We have a 3-stage productions. We start from a 2-dimensional magneto-optical trap that is used to load a 3-dimensional magneto-optical trap. And then from there, the atoms are transferred into a quadruple trap made of 2 pairs of coils that are moving along this direction. So we move physically the atom from this side to what we call the science cell, and here we transfer the atom to a much smaller a trap made with smaller coils that enables us to reach higher gradients. And we do this because we want to have differential pumping stage at each part of the experiment, and this allows us to achieve very long lifetime of the order of 2 minutes in the last chamber. So our glass cell that you can maybe see on this picture right here, there are many coils around because we use in the end, purely magnetic trapping to trap the atoms. And we start in a quadruple trap, so a trap with a zero of magnetic potential energy at the center, and we trap weak field seeker atoms. And because of Majorana spin flips in such configuration, we use an optical beam to plug this trap, so it's a very well-known technique. And the specificity of our setup is that at some point, we load the atom in a purely magnetic trap made of adiabatic potentials. So we use radio frequency dressing of the magnetic trap to create avoided crossings that confine the atoms on an iso potential of the magnetic field. And because we use an inhomogeneous static magnetic field that originates from quadrupolar coils, we have this ellipsoid geometry of the isopotentials. So at first, when we condensed in the plug trap, we see a very dense cloud in time of flight. And then when we transfer in the dress trap, we see that the shape of the cloud, always in time of flight images, changes. And this already indicates that the cloud is more strongly confined in the vertical direction. And if we push the parameters, so the magnetic field gradients and the properties of the radio frequency, we are able to create very elongated traps in time of flight, which means that there is a very tight confinement in the original trap at the beginning. And we are able to prove that almost all the atoms occupy the lowest harmonic oscillator level for the vertical direction in this case. So we have a quasi-two-dimensional gas. So just to give you some numbers, we are able to achieve trapping frequency of the order of 2 kilohertz, and we can tune the geometry of the in-plane potential with typical value of frequency in the range of a few tenths of hertz. And the last thing I would like to mention is that we are able to control the temperature of the system using what we call a radio frequency knife. So this is another tool we use to truncate the potential at some energy that will allow us to control the temperature in the system. Okay, so with all this, I would like to go now to the first results, experimental results. See how do we obtain this kind of images that are that we claim are the collective modes of the system. So when we load our trap, if we do it in a non-adiabatic way, too fast, we will typically have an excited cloud. So what I mean is that if we repeat the experiment, each time we do the experiment, we take a picture, and this picture gives us information about the state of the system. So this is an in situ image this time. So this is really the density distribution inside the trap seen from above. And if we repeat this experiment many times, we will see that the cloud is moving a little bit, that the shape deforms, and so on. So how can we identify what kind of modes are excited in such a situation? Well, we do this using studying the statistical correlations between the pictures. So this is a kind of original method. So one way would be to try to fit the density profiles with some theoretical curve, but we try to obtain this collective excitation in a model-independent way. And the thing we do is that we compute first the average picture that will give us an idea of what is the more or less the equilibrium state of the gas around which the excitations are. And then we study the correlations between the density deviations with respect to this average picture. So we build this matrix that is a correlation matrix between the deviation at some position and the deviation at another position, and we average over time. So we want to see the system evolve, so we take pictures at different times and we average over all these pictures. And as you can see, this can be put into the form of a real symmetric matrix, so we can diagonalize it. And when we diagonalize it, we obtain what is called, in fact, in this, so this process, this statistical analysis has the name of principal component analysis, and what we get are the principal component. And this principal component can be put into the form of pictures again, and they tell us what are typical correlations in the pictures. So, namely, mainly how do we interpret these principal components is by saying that, for example, this one, it is, when you see red here, it means that there are more atoms, and blue, there are less atoms. So we have correlations in these directions that says that when the gas moves towards this point, there are less atoms there. So this is associated to a kind of global center of mass motion of the cloud. And we can find, in general, we find two of these modes that have orthogonal axes that describe two specific motion modes of the gas. And in fact, we can identify these modes with what we call the dipole modes, so the sloshing motion inside the harmonic trap. And what's interesting is that if we look at all the principal components, we can find other principal components that are maybe more interesting. So the first one, for example, this one, what we call monopole-like, is a component that describes how, when you remove atoms from the center of the cloud, they redistribute to the edges. And this is, so we call it monopole-like because we have reasons to do so. And the thing is that this kind of mode allows you to probe the compressibility of your system because it's sensitive to the density at the center of the cloud. And the other interesting mode we find is what we call the scissors mode, and I will use it in the rest of the talk to characterize the superfluidity of the system. So this guy has correlations that are at the same time x and y. It means that when you have a positive x and y, so atoms missing here, you have also atoms missing in this quadrant, and the atoms move to the other two quadrants. Okay, so I talk about principal components and modes. Can we prove that there are indeed modes of the system? What we can do is use them to now decompose each image as the mean image plus a decomposition on all these principal components, and then follow, for example, the value of the first coefficient in this new basis. And if we do this, we can see that some of the modes exhibit very regular oscillations, and we can fit this to sine curves, for example, to extract quite precisely the trapping frequency, for example. And for the scissors mode, we see that we have a more complicated time evolution. Okay, so, yes.
Since the GP equation is nonlinear,
Yes.
it's not obvious to me you can write this as a sum of modes.
Okay, so the point is, it's true that the GP is nonlinear, but we are here talking about weak excitations. So you can linearize the equation around this, this average density, yes. Okay, so now I would like to talk a little bit more about the scissors mode. So the scissors mode has been proposed by theoreticians to study superfluidity of the trapped post-gas. So the idea is that this kind of XY correlations, if you think of it as a small density perturbation, will give you, in fact, an oscillation of the long axis of an anisotropic cloud. And you have predictions from theory that you have a given specific frequency for a superfluid, and for a normal gas that is more or less collisionless, in the collisionless regime, you don't expect a specific mode. You only expect, as you mix X and Y components, to have the bit nodes between the trap frequencies. So frequencies that occurs at plus and minus the trapping potential, the in-plane trapping frequencies. So, So that's a very good question. So this one is particularly convenient. Other modes can be used, and for example, the quadruple mode also has a specific features for superfluid that you don't have for a classical gas. Okay, so we will try to use it as a signature of superfluidity across the BKT transition. And in some sense, this is why I said it's like redoing the experiment in helium, because here we really probe the way a kind of pendulum that is oscillating around the vertical direction will react to the presence of a superfluid. So what do we expect? So the experiment has been done for a three-dimensional gas in the group of Chris Foote in 2001, and what they have seen is that for Bose-Einstein condensate, this time when you are so well into the Bose-Einstein condensate regime, you see a single frequency that is at the expected Sizos mode frequency, and when you go above the transition, you get the two normal mode frequencies, and in between you see some strange behavior where the three frequencies coexist. For two dimensions, there have been some numerical predictions showing that you should see a continuous shift of the frequency across the transition, and at some point the appearance of the low energy, the low frequency oscillation. So what do? We now try to control the initial point, so we load more carefully the trap, so the cloud is at equilibrium in the beginning, and then we suddenly rotate the trap axis to induce this oscillation of the Sizos mode. So then we follow what the theory told us. We compute the XY correlation in the system, and we plot the time variation of this system, and we have from the theory formula to fit to this observable. And we repeat this for various values of chemical potential and temperature to try to span the transition. So typically we see when we are well in the superfluid phase, we see a single damped oscillation that is quite nicely fitted to the theoretical formula. And when we are above the BKT transition, we see a more complex oscillation that is also, we believe, quite well described by the theory. Then things get a little bit complicated, because when we try to analyze all our data sets with respect to what we expect for two-dimensional system, we see that we have kind of not a clear picture, where we can see at some point, for example, with almost the same reduced chemical potential here, we can see a response that is mostly superfluid, and in some case we can see also for another data set the two frequencies of the normal phase appearing, or some frequencies in between. So this was a little bit disappointing. We tried to have a more careful look at the data, and I will try to convince you that in fact we are able to understand what happens there by looking at three specific situations. So 1 point above the BKT transition, so where the fluid is normal, 1 point deep into the BKT regime where we see only the superfluid frequency, and 1 point in between, so the one that is circled in red. So what's the problem? The problem is that in this system, in this trap system, we know that we have a superfluid at the center where the density is high, but in the wings of the distribution, we know that there is also a normal fluid. And when we try to fit the whole correlations of the system, there could be a competition between the signal from the normal phase and the signal from the superfluid phase. So everything gets mixed together, and then it will depend on the signal-to-noise ratio to discriminate which signal we have in the end. So the idea we followed was to try to have a more local analysis, and in the spirit of the local density approximation, try to see if the dynamics at a given density, so close to a given value of the superfluid fraction, for example, was more clear to analyze. So we cut our samples in thin annulus like this, so slightly ellipsoidal, that follow, in fact, an average value for the density in the system. And when we do this and we try to compute the contribution of this part of the system to the XY correlation, we see oscillations and we can extract frequencies from this oscillation. And now you will see that we have a much clearer picture. So the idea is that for our point where we know that we have almost only a superfluid in the gas, we see that whatever the radius we choose, we always get the superfluid frequency. So there is a single response in the system. When we look at the point where we are above the transition, so we expect only a normal part contribution to the gas, and we see that mostly it's true. The outer edges of the cloud oscillate at the expected frequencies, but it starts to deviate as we get into the closer to the center where the density is higher. And for the point in between, we see this nice crossover in the dynamics where the central part of the cloud seems to oscillate at this scissors frequency of the superfluid, and the outer part oscillates at the normal frequency or close enough to the normal frequency. And if we try to compare this to what we expect, yes? So the error bar here, so what we have is we have a formula to fit this XY observable that is given from the theory. And in fact, the three parameters of this fit are not, for example, the frequencies of oscillations. They are kind of hidden parameters that we fit, and these parameters give you the frequency. So it's so another way to say it, maybe more clear is that the fit is constrained. The formula.
That's what I saw when if you look at the curve that you have, not just one single sinusoid.
Yes.
You have to put some kind of additional functions in order to fit this, right?
So this is provided by the theoretical formula, and this formula is just constrain the frequencies and the damping, in fact, of the different oscillations. So when we feed the data, we get a confidence interval on those parameters, and from this confidence interval, we extract the confidence interval on the frequency. So the meaning of the error bar here is that if you see, for example, this point here with a maximal error bar, it means that we are not able to extract a frequency from the signal. And when you see very small error bars, it means that the signal is very close to what you expect from the theoretical formula. So it's okay. The wider the error bar. Yes. Yeah. According from theory. No, it's a confidence interval from the model. Yes.
So what it means is if I see a small error bar, I can say you measure the expected frequency. If this bar is large, that means you don't know what to measure.
Exactly. So we don't claim that we see, for example, a crossover between the two, and because this kind of effect could also be linked to the fact that we average over some size on our sample when we analyze the gas, and then if this average takes into account both normal and superfluid response, we don't know exactly what we are doing. But what we see is that if we compare to theory, we see that we more or less are able to identify in this way where the transition should occur. So it's not from equilibrium measurement, it's really from the dynamics of the system. And just to comment on your question, in a more recent work, we used principal component analysis also to show that in a model-independent way, just by studying the correlation in the system, we are able to show that there is the outer part of the cloud contributes to okay. There is no correlation, if you want, in the dynamics between the inside part and the outer part, and this is without relying on the theory. Okay. So I would like to now come to the last part of my talk. I will try to go fast. And I will just like to show you how we are able to create this, what we call the long-life supersonic superfluid in our system. So briefly, why do we want to rotate our gas? It's because of this analogy, because between the ideal 2D trapped, harmonically trapped rotating atomic gas and the 2D electron gas in a uniform magnetic field that exhibit quantum Hall effect. So the idea is that if you study this Hamiltonian and you start to increase the rotation frequency, you see that the levels will get highly degenerated at exactly rotation frequency comparable to the trap frequency, and this is what is called the Landau level structure. And the idea is that once you have a highly degenerated ground state, then you probably will get out of the mean field description and have more, let's say, exotic states. So we would like to realize experimentally this kind of system. So we do this by, again, controlling very carefully the cloud geometry, and what we are able to do is introduce a small anisotropy in the trapping potential and then make the axis of this anisotropy rotate at a given frequency. And what we know from this is that this kind of excitation will couple this time to the quadruple mode of the system, and for given specific steering frequency, we expect to be able to transfer rotation into the gas. So this we can do if we rotate exactly at the, let's say, the good steering frequency. We can create a kind of a vortex lattice. If we increase slowly the steering frequency, we are able to put more vortices in the system, so more rotation. And at some point, we start to see that the vortex lattice that is quite nicely triangular in the first place becomes a little bit disordered. And as we increase further and further the rotation, the steering frequency, we see that the picture gets less clear. And I would like just to contrast these measurements with what has been done in the NS group almost like many years ago. So they did the same experiment, so the figures are a little bit different because the traps are different, in a 3D gas. And what they have seen is that they see that the vortex lattice disappears for this kind of protocol of steering the gas. And in their case, you can attribute this to the fact that as you rotate faster and faster, you will be able to excite, to bend, in fact, the vortex line in the 3D gas, and then probably reduce the visibility of the vortices because of you get a kind of a tangle of vortices in the end. In our case, it's a gas that is close to a 2D gas, so in fact the vortex lines always remain straight lines. They are not allowed to bend. So what can we do with this? What we see is that we probably have a melting of the vortex lattice. We don't know yet. We have to do quantitative studies. And this is expected in 2D due to the long-range phase fluctuations. And this is, in fact, if we want to have not to have this kind of melting of the vortex lattice, it requires to have very low temperature in the system. And what we can see is that we are always, even when the vortex lattice disappear, we are always in the diffuse vorticity regime, meaning that we got, for those kind of large number of vortices in the system, we got almost solid body like rotation, and this we can probe by letting the cloud expand and measuring how it expands, and we see that it fits nicely with a solid body rotation. So how do we reach higher rotations, and we are confronted to a problem that in the naive picture of the rotating harmonic trap, then the centrifugal force will eventually cancel the trapping potential, and then we will lose the atoms. So what happens, in fact, is that we have higher order terms in our potential, and in particular in our kind of bubble trap, we have this kind of higher order terms of lambda times the radius to the fourth term. And what will happen is that when the cloud rotates exactly at the trap frequency, we get a flatter potential, but still a potential that will be dominated by these terms. And if we go now beyond the trapping frequency, we will obtain this kind of effective potential in the rotating frame with a double well rotating minima. So this was already studied many years ago, and in particular, what has been shown is that if you excite this quadruple oscillation and you are able to put enough rotation in the system, you expect this kind of dynamics where you create a gas with a central hole in the center. If you are interested in the what is the ground state, when you increase the rotation frequency, you expect something like this. So at low rotation, vortex lattice. Then when you increase the rotation, you will see that the vortices will start to merge and form a hole in the center. And this hole, in fact, has a multiple vorticity. And if you are able to reach sufficiently high rotations, then you will be able to expel all the vortices from the bulk of the system. So all the vorticity is now inside this giant central hole. Okay, so can we do this? So in our experiment, we expect more something like this, mainly because the fourth order term on the potential you see has a very different value in the same units than what has been studied in theory. So we have a much weaker quartic term, so we expect to have a much larger effect, if you want. So the radius of the hole will be larger, and also we need more atoms to observe the effect. So we still expect more or less to have this kind of vortex lattice. So we don't see this in the experiment, but at least what we see is that when we increase the rotation frequency and we steer the system for some time, after stopping the steering procedure and letting the system relax for some time, we observe the spontaneous formation of not quite really a hole in the system, but we see that the atoms tend to localize on a given radius. So there is, so the atoms want to go there because it's in the rotating frame, it's the trap minimum, if you want. And this is an indication that we have reached effective rotation frequency that is above the trap frequency. And yet, when we steered at a frequency below the trap. So what happens? There is spontaneous kind of acceleration of the rotation. And in fact, so this is surprising, but in fact, it comes from our weak Aref knife. So it turns out that our radio frequency evaporation is more efficient at the center of the trap. And when the gas is not rotating, we don't care because in fact, this effect, we don't see it because the gas is so small. But now that we rotate, the gas expands and is allowed to probe more different places into the trap. And now we are sensitive to this effect that, in fact, the evaporation process is more efficient here than there. And then, if you think a little bit about it, here you will remove mostly low orbital angular momentum states. So we have a kind of selective evaporation also in the orbital angular momentum angular momentum basis. Here probably artifact of the optical system, I would say. Okay, so this is preliminary results, but what I will show to you is that if we now try to evaporate more, so lower this knife, just to check what I'm saying, we will see that we are able to increase indeed the rotation. So we can see that we are able to create now a gas with really a huge depletion in the center. So we are now sure that there are no atoms in the center and that the ring radius has increased a lot. And we are able to extract the effective rotation frequency, and we see that we are well above the criterion where the theory tells us that we have this kind of giant Hall effect should occur. And we also see that as we remove atom, as we evaporate, the width of this annulus is getting thinner and thinner, and we are close now to the optical resolution limit of our system. Okay, so what can we say about this fast rotating cloud? So first, we have a large angular momentum per atom of the order of 360. And the most surprising thing is that if you compute the linear velocity of the gas, you find that it's rotating at 10 times the speed of sound. So it's rotating extremely fast for a Bose gas. And we are currently probing the collective modes of this annular-shaped gas. So we have seen monopole modes, quadrupole modes of this system. So excitation, we are able to do spectroscopy. And we are looking for beyond mean field effects in the frequency of these modes, just to see if we are able to evidence them. And I would like just to say one more thing, is that if we now go back to this lowest Landau level picture, where are we? We are in a situation like this, so we are rotating faster than the trap frequency, and due to the quartic term, now the levels, the single orbital levels are like this. And it turns out that our chemical potential is around there. So we have mostly atoms occupying the lowest state here, with quite a high degeneracy around on the minimum point, where there are many states that have almost the same energy. So let me just summarize what I've shown in this talk about superfluid dynamics and so the direct observation of the collective modes in the trap, how we use the Sizer's mode to evidence the superfluid response of this two-dimensional Bose gas, and the current work we are doing about fast rotating Bose gases. And I would like just to thank the people that are doing the work in the group. So we had many PhD students on this experiment. So one of the first was Karina Merlotti, that was here at USP many years ago. Then Camilla De Rossi, Mathieu De Guer just defended his PhD thesis, and he worked with our postdoc Avinash Kumar, and now it's Liang Guo that's running the experiment. And with this, I thank you for your attention. So, as you probably know, in fact, truly to have beyond mean field effects in such systems, what you need to have is, let's say, a number of atoms that is comparable to the number of vortices. So when I say LZ of the order of 400, say, it means that you expect to see the exotic states associated to quantum Hall effect and things like that for atoms number like 4,000. And we have 10 times more. So we are still, we have too many atoms if you want to see really exotic states. But there are some theory papers that claim that you can see maybe in the excitation spectrum of the gas, like precursor, if you want, of these states, and that should be more robust to the fact that we have many atoms. So if you want, there will be still, so namely, you expect some kind of frequencies for the mean field, some other frequencies for the strongly correlated states, for example, for the collective response. And the way the crossover occurs between the two regimes, it's more favorable to observe it when you are not quite into this deeply correlated states regime. So there is hope to see deviations in the frequencies of the mode that will be associated with this kind of effects.
I understand. You are in the bubble trap.
Yes.
So you are in the bottom of like a sphere, right? And then you have a very thin edge and a more thick center.
So
it's you have a disk, right?
In
the bubble.
So when we are rotating,
that's
we expect something like this.
Yeah,
yes.
yeah. If I look at the profile, the side view.
Yes.
So why is that flat in both bottoms? I mean, I was expecting. You know what I'm saying?
I'm not sure.
Okay, the side view.
Yes.
I'm imagining that's the bottom of a sphere.
Yes.
And why is that flat?
You mean?
Yeah.
Here?
Yeah.
So
it's a curiosity. Why is that flat? I was expecting that to follow the curvature.
Yeah. So you don't have. So in fact, the potential, if you follow the potential, it will be like this. So with a curvature, but you don't have atoms here anymore because of the rotation.
Oh, that the rotation then put the little bump in between.
Yes.
Right. Okay, yeah. It looks very flat.
But
okay. Well, it's
it is.
curious. I thought, yeah, maybe it's the projection. Yeah. Sorry.
Yeah, I had a couple of questions. One is, I don't think you mentioned this 2D scattering length, which is like logarithmic in the or exponential in the phase shift. Does that not come into your analysis?
No. So we are into the regime in which I forgot to say it on one of the first slides. So for us, 2D means we don't have enough energy to excite the vertical harmonic oscillator. And that's it. I'm meaning the collisions, they are still 3D. So the only effect on the collisions is the renormalization of the interaction strengths by this A over AZ. So you have to compare the lengths of the S-wave, 3D S-wave scattering lengths to the confinement lengths in the vertical direction.
No, but as long as you have no excitations in the transverse direction, you can map everything onto a 2D scattering length, I thought. You're saying that's not true?
So what I'm saying is that if you want to reach the regime in which you see two-dimensional collisions with indeed redefinition of the scattering lengths and so on, you have to go to much stronger confinements.
Yeah, I don't see why. If you're in the lowest transverse mode, I don't think that's true. Well, no, but that's a resonance. If you could be away from the resonance and still have 2D scattering.
I'm not sure. There's something in between, I think, yeah? A regime in between.
Yes.
Strictly 1D or strictly 2D and just occupy only the transversal ground state.
The energy dependence of a scattering process does depend on the large distance behavior, right? And in this case, the large distance behavior, it is 2D, even though the confinement, it's finite. Right? When the atoms are a very far distance, they see that confinement. It is always almost a 2D problem. So I would think that you should have some 2D physics and the energy dependence on the S-wave scattering length. But I guess maybe I don't remember even seeing a. Well, that's what Roshani does, right? Yeah, the Horta Bloom. Yeah.
Yeah. So if you
Yeah.
take the formula by Olshani, what you see is that if you plug so I think the formula you are referring to, this correction is in fact really small because there is a factor of so this ratio of AS over AZ occurs somewhere, and this kills the next order term. So at least in the experiment, we don't have by any means the resolution to see those kind of effects. It's very small effects for us.
The second question I had was, do you think you could go to smaller particle number and really see things like the Laughlin 1/2 state for bosons or the integer Hall state?
So in principle, it's possible, but it means that we have to rebuild the experiment because we will need a much higher detection. I mean, detection scheme with a much higher sensitivity, and right now we don't have it. Yeah.
If you have a giant vortex, the superfluid velocity around the giant vortex should be increased. And if the superfluid velocity exceeds some critical value, the temperature may be increased. Can you observe that?
So one of the experiments we would like to do is know that we have this kind of. Okay, what I can say is that right now we probed this system by using very smooth deformation of the trap because this is what we can do easily with our setup. So we have studied the monopole excitation, quadrupole excitation, so excitations with a very long wavelengths along the ring. And what we see is that we can excite some modes, and that these modes have very slow relaxation, for example. So we see the modes evolve for maybe 60 seconds, for example. And then one thing that would be very interesting to do would be to add some disorder or add a very localized defect onto the system and see how this couples to this gas and what kind of excitations it produces. And this it's one of the things we want to do, yes.
The whole point of quantum turbulence, the quantification of that, is still an open question. And that's very interesting, I think. We also heard about, about simple models that you could do them, and you learn a lot of things, like the Hubbard-Bose model, which allows you to study many body effects. And of course, we heard a lot about Efimov trimers and the way they make the transition to Feshbach dimers per atom. Of course, the question remains, what happens to the other channel which is there, namely the trimer going to three atoms, without, for example. And we heard about the dynamics of Rydberg spin ensemble, and that was quite informative. I mean, and so all in all, it was a very nice workshop. The idea is to learn these different things and to exchange points of views which are quite different, and you end up leaving the venue with something more, you learn something, which was quite really nice. And so I thought I may have this session to see if somebody wants to make a comment or whatever, raise a question. So it's up to you. Anybody? Okay. That's right, yeah. Absolutely. The talks as well as the photographs, you know. So they will put them there. And if there are no questions, I'd like to, oh, by the way, I'd like to thank my co-organizer, Vanderlei Baniatu. I enjoyed very much working with him in organizing this, and I thank him very much.
We don't need microphone. I just want to thank you all for coming. It's a different type of workshop, a small group, and the idea is to know better each other. Maybe from here start to contact, because now we know better what people are doing, and I hope you return to Brazil. We have many different things going on here. In Cold Atoms, we have another meeting in June, end of June, beginning of July in Natal. And our International Institute of Physics in Natal also is open to proposals for workshop organized by outsiders. So if you want to organize a meeting in Natal, the International Institute even provides some support if it is a good proposition, right? So hope you guys enjoy and maybe return in the future with new initiatives in this field, which is very far from saturated, seems to be. So thank you all for coming, okay? And thank you, Hussein, that was the real chair of the thing and sending message everywhere. Thank you.
Before, of course, ending this meeting, I'd like to reiterate what Vanderlei said, thank all the speakers for coming here and telling us about their work. And I hope you'll have a safe trip back home. And please, I remind you to send me a copy of your boarding pass for the trip back.
Otherwise, you go to jail.
I know, that's the point. And of course, I'd like to thank the Institute for Advanced Studies here at the University of São Paulo for giving us the support and being so generous. And last but not least, I'd like to thank the secretary of the meeting, Ms. Claudia Regina, for helping us organize the meeting. And as a sign of appreciation, I'd like to call her to give her some Easter chocolate, you know.
Eu chamo vocês de Grupo das Estrelas. É um prazer recebê-los todo ano. Muito obrigada, viu?
So with this, I close the meeting.
But first, let's thank Mahir and Vanderlei.